I hope something good was said about me. I don't understand Polish. So my name is Vinod Joseph. I work for professional services in EMEA. I basically handle what we call as the packet optical convergence, the products and solutions within Juniper. Primarily, my area of focus is around the Juniper PTX product. How many of you know about the PTX? Have you heard about it? All right, okay. So the PTX, in a sense, is actually our next-gen core platform. It is about 480 gig per slot. It is a pure label switch router, which means that it doesn't carry a lot of the edge functions or edge features and so on and so forth. It's something which is highly sophisticated in a sense where it gives you high performance, something around 4 microseconds in terms of latency on a per node, if you may. Today's presentation, I think we'll try and focus on what we essentially did for the London Olympics. What was our role within the London Olympics as Juniper, and what exactly did the PTX actually do as far as the London Olympics went. I'm not sure how many of you are aware of the London Internet Exchange. Now, LINX actually is one of the largest internet exchanges world over. If I remember correctly, it carries close to 1.6 terabits of traffic, right, aggregate. Now, LINX actually is a non-profit organization. It essentially is an interconnect point, which means that you have multiple carriers like the BTs and DTs and FTs, even the AT&Ts, if you may, who actually interconnect with the LINX infrastructure, and they actually form BGP peering sessions with each other. Is everyone familiar with what an internet exchange is? Is that something which? So typically, what an internet exchange like LINX does is that it offers a virtual LAN, if you may. It offers a layer 2 network to all its members. And when I say members, it's actually all of the carriers, like I said, the BTs and BTs who are LINX's customers. LINX actually has been growing pretty much year on year. I mean, they were like 800 gig, if I remember, in 2010, and today, if you look at their aggregate traffic, we're talking about close to 2 terabits. And in fact, there's a lot of competition between LINX and the Deutsche Internet Exchange on who's going to become the largest IX in the whole world. So that's where LINX is at the moment. Before we get into the Olympics, pre-Olympic era, this is what LINX looked like. So, like I said, you have multiple locations or multiple points of presence, and they had 2 distinct LANs or 2 distinct networks, as they call it. One was essentially an extreme-based network using extreme switches. The other was typically using Brocade switches. So what it meant was you had different members connecting their routers or equipment actually at each of the switches, depending on their location. For instance, we may say that this was located in Telehouse, which is a point of presence in the UK, in London. So, for instance, BT would have a POP there, and they would interconnect their fiber straight into their LAN, into the switch there. Similarly, you had a second LAN, which was primarily for having physical layer redundancy. In other words, all the members actually insisted, when LINX was formed, that they need to have 2 distinct networks, so that if one network fails for whatever reason, you have another network. The second primary objective was to have a different vendor on a per network basis. You have Brocade, and then you have Extreme on this side. And if you look at it, Brocade has been very, very active in the Internet Exchange community because I think from the days of Foundry, they essentially were very popular in the high performance layer 2 switching environment. Now, what were the challenges LINX had? Essentially, any layer 2 environment, it's very easy to say that a layer 2 environment is all I need to actually provide points of interconnection. I just plug in the members, I create a huge layer 2 LAN, and I leave it up to the members how they manage their BGP sessions. It's the easiest way, it's the simplest way, yes. But I think one of the challenges that people like LINX had was, as they started growing in scale, the demand for better service was something which started coming from members. In other words, if you have a traditional layer 2 LAN, what are the challenges you have? You typically have spanning tree issues, right? So what does it mean? It means that if I have any two links in my network, only one link can be active. My second link will always be on standby, right? So coming back to one of the LANs which is of interest, the Brocade LAN, which was the largest LAN carrying most of the traffic or the bulk of the traffic, they say to find out that the ring protocol which they used, Ethernet ring protocol, I think there was a gentleman who was presenting about the extensions to ERP from Extreme. No offense to that, I'm not sure what the enhancements are at the moment, but...
Excuse me, is there any problem for you to use the microphone?
Can do that, sure.
Thank you very much.
Yep. Is it better now? All right. So at that point in time, ERP was not very simple. I mean, at least LINX said, we find it very, very difficult to manage. Convergence is a big issue for us. We don't see that. The other issue is lack of ECMP. ECMP is equal cost, multiple paths, right? So if I have 2 or 3 links, which are of equal cost between 2 pair of nodes, I would like to achieve load balancing. Now that was not there, because with traditional ring protocols, you had a active standby behavior. You couldn't have a active behavior. So not to mention, I think they had some issues with code and stability and so on. So Juniper grabbed the opportunity and we went and we sold our MPLS story, and we said MPLS is the best thing to do. And why not choose MPLS? So we talked about the advantages, and we said we have carrier-grade equipment. Let's re-engineer your network, and let's make it completely layer 3 based or MPLS based. Let's get rid of your traditional ring protocols or spanning tree protocols and so on, and move into something which is more interesting, which is more deterministic. I think when I say deterministic, it means that the ability to provide an operator or an exchange with the clarity about how traffic will flow under a given circumstance, which means that if I don't have any failures in my network, I should be able to determine how traffic will flow from point A to point B. And if there is a failure, I should also be able to know how traffic will fail under a failover circumstance. Now, why is it very important? I think for an internet exchange, it's very important because you don't have a large network in terms of number of nodes. What you have for an internet exchange is lesser number of routers or switches, but big, fat, and thick pipes between each of them. So if you go back to this slide, you would see that network 1, which was Brocade, you have hardly about 10 or 12 nodes, and typically you have these fat, big pipes between them. So you might have like 16 into 4 10 gig links or whatever it is. So huge bundles of links. So it's very important for people who are operating the network to understand where and at which point traffic will go through which link. So that's what we meant by saying make it more deterministic. So phase 1, what we did was evolving the network, again, pre-Olympics. We sort of offered a Juniper MX-based solution, which meant that you replace all of the Brocade switches with Juniper MX 960 routers with 10 gig line cards and so on. The virtual LAN was something which we offered through VPLS. So you said you need a virtual LAN, you have a single VLAN for all your members, create a single VPLS instance using BGP VPLS, of course, because we as Juniper love BGP. So we did BGP VPLS for them, and we actually emulated that environment for them. Now, we also gave them the ability to use traffic engineering, which meant that you can actually create a much more deterministic behavior, which I said, in how traffic flows within your network. And how do you achieve that? Typical schemes within TE, like using link coloring is one example, where you can say, I color a set of links. If I have 20 links in my network, I color each of those links as orange, blue, red, or green, or whatever, and then I define constraints within my label switch path. So I say, between point A and point B, if I need traffic to go, under all circumstances, it should only use my link which has a color of, let's say, orange, right? It should never use any other link color. So it kind of gave them more granularity in choosing which is the best way of steering traffic between a given set of nodes. Operational complexity is one thing, because whenever we talk about having all these sophisticated schemes of link coloring and so on, how complex does it become, to manage and operate? So again, coming back to the slide earlier, an internet exchange, like I said, is a much more smaller environment in terms of number of nodes and number of links. So that makes it relatively static. So you define it once and you just configure it and let it work. If you're talking about a network which has 5,000 nodes and equally double or triple the amount of links in that, would I recommend link coloring to actually achieve deterministic traffic behavior? I think you might go nuts. So I definitely wouldn't do that. So I think the requirement was such that it kind of fitted into what they were looking. So it turned out to be this. Again, a complete replacement of the Brocade infrastructure with MXs in here. Let's quickly move on to some interesting aspects on migration. The most important thing is nobody can migrate an entire network in one maintenance window, right? It's something that you do over a period of time. So how do you evolve a migration strategy which can coexist with your existing equipment? Which means that when I introduce a new piece of hardware, that has to interoperate with the older piece of hardware or the existing piece of hardware, which is Brocade, and at the same time, the service infrastructure is different. The Juniper PEs are going to be running VPLS/MPLS, and you're going to have the Brocade side, which is going to be doing pure layer 2 switching or bridge domains, if you call it that way. So a couple of options that we discussed on the table was, number one is, put the MX in as a traditional layer 2 switch, let it do trunking on the VLANs, carry whatever VLANs are responsible, enable intra-VLAN communication across the different set of equipments, and then virtually start migrating each members onto the new equipment, which is the MX, and finally actually start creating the VPLS infrastructure. So, a two-step procedure was what we thought of. Was not the greatest of ideas because we said, why do we want to keep the existing service instance? Why don't we just put VPLS on the MXPE and at the same time have the Brocade switches interoperate with the MX? So the obvious question is, can I have VPLS on one side catering to a set of VLANs, and can I have a traditional layer 2 switch on the other side catering to the same set of VLANs? Can I still have connectivity between both of them? The answer is yes. So VPLS, I think one of the things that people misinterpret is that the moment you add VPLS, you're bringing in an MPLS component or an LDP/BGP component, which means that if you're not able to have a peering relationship between the Juniper PE and the Brocade switch using either LDP or BGP, you will not learn MAX, but that's not true. The simple aspect to be considered here is that VPLS learns MAC on the forwarding plane or data plane, not in the control plane. You don't learn your MAC addresses using BGP. You learn it in the forwarding plane through flooding, for instance. So even if you don't have your LDP or BGP sessions up, so you can still have one side running VPLS and the other side running traditional layer 2, right? So that makes it much more simpler. The other point is, what will the upstream interfaces be? If I have VPLS on my Juniper PE, are you saying that all my trunk interfaces upstream into the core should be MPLS, or can it be layer 2? It can be layer 2, right? So this was the migration strategy that we adopted in gradually transitioning VPLS to replace an existing layer 2 infrastructure. Coming back to the most important aspect is 2012 London Olympics. 2 months before that, we had this meeting with the customers, and we were talking with many of our customers like BTs and LINXs and so on. And one of the thing was, most important aspect was we need more bandwidth, we need more capacity, we need more density on the chassis, and at the same time, it should be risk-free. So what do? Do we actually live with the existing platform? The MX960 has a limitation in terms of how much it can scale. So if I'm going to really cater to the kind of bandwidth requirements that LINX put on the table, then I'm talking about adding probably another 10 or 15 MXs, which means it's more operational overhead from an OpEx point of view and a management point of view. So we took a kind of bold move and said, why not look at a chassis which is very recently introduced into the market. Probably you guys are going to be the first guys, the guinea pigs to try it out, but it's worth trying it out. So we said, why not look at a packet optical platform, which is LSR only, which is not IP routing, which is pretty lean in terms of the power it needs, which is pretty mean in terms of the performance it gives you, and it typically has a lot of port density on it. So it means that if you're going to compare the MX versus the PTX, for every 2 MXs you can just have probably 1 PTX, or for every 3 MXs you can have 1 PTX in there. So that was the kind of plan that we had. Was not accepted very well by all of the members because LINX does not take decisions centrally. It's taken by a board which comprises of its biggest members. So you have people from the BTs and DTs and so on who are sitting on the board making the decision, and we really had to kind of go ahead and convince them that this is something we can look at, and this is something we can deploy for them in a timely way. Just for your information, I'm not going to get into product details and try and sell a platform here, but this is what a PTX is: 8-slot chassis, 480 gig per slot, a pure LSR platform. Can do IP routing, yes, but it's built customly for catering to label switch traffic, and basically supports all of the traditional MPLS features, including pseudo wires. Now, one of the things I should admit here is that the PTX as a platform essentially cannot do deep hashing on a layer 2 frame, which means if my traffic is pseudo wire traffic, or if my traffic is going to be VPLS traffic or layer 2 traffic, I cannot do deep packet inspection and hash based on the information available. The simple reason for that is that PTX was designed to be a platform which is cost effective and at the same time is something which people can afford to deploy. We don't want to bring in a platform here which is extremely costly and make it incredibly complex for somebody to put into their network. So what did it mean? It meant that now if I'm going to remove the hashing functionality, right, from the aggregate Ethernet interfaces in the network. So I forgot to mention that LINX has huge lag bundles between any 2 set of nodes. So now if I'm going to put in the PTX, it means that I have to break the lags. So is that a good idea? One of the other things before I get into saying how we did it was, if your traffic is a mix, for instance, layer 2, layer 3, IP, whatever, then hashing is fine because it would even out. But if it's, like I said, pure layer 2, like an environment for an internet exchange, then you're going to have the issue with lag bundles. So we said we have to break lag bundles. And the honest fact here is that we didn't try to kind of undermine the capabilities of lag bundles or AE hashing with LINX, because that is what we had deployed in phase 1. So now if we go back and say, remove lags because it's a bad idea, then I think that's not going to sell. But the honest fact is, and this is again very, very specific to Junos implementation, and the way we actually program the internals here, is that AE bundles traditionally have been very resource intensive, at least based on my experience on Junos. Very simple reason. When I have a set of next hops, let's say I have 4 links, right? 4 physical links. What do I have in my packet forwarding engine, right? I have a set of next hops. So I have one next hop pertaining to one interface, second next hop, third, fourth, and so on. If I use AE bundles, the amount of next hop index space or next hop address space that gets used up is humongous. It's huge. Again, I've given you an example here. If you look at the example here, you have, if I have a router which has 10 physical links, no AE bundles, I would have 10 next hop indexes used, or 10 next hop entries. Instead, if I use a AE bundle with 10 links, it gets multiplied into 10 into 1 plus 10. So I have 10 times the number of next hops I'm going to have. So I'm not going to get into much detail here, but all I'm trying to say is from a resource perspective, it was again pretty costly. So now the whole objective is, if you're going to get rid of your AE bundles, then what is the way of actually achieving hashing in the way they have been using it currently? The industry actually, I'm not sure if you're aware of this, there are two solutions which have been talked about largely in the industry. One is the use of fat pseudowire and entropy labels. Now what does that mean? That means that at the edge, if I have a device, now what I can do is I can use a particular label, right, to identify a flow. So if I use, let's say, label X for flow 1, automatically the neighbor router or the LSR can use that particular entropy label, as you call it, and say, okay, this belongs to flow 1, so I have to put it on a particular link. Similarly, you can have another flow with a different label. So I can do that function completely at the edge and then have the core router just look at that particular label entry and appropriately achieve the same kind of granular load balancing, if you may, that AE hashing provided. Was too premature a solution at that point in time to try out, so we did not do it. The other was a very new draft which is written by a gentleman that all of you might know called Kiriti Kompella, and I'll talk a little bit of about that draft. Again, that was pretty premature to deploy. So we said, let's be honest now, you're going to put in this platform which is going to scale, which is going to give you what you need, but you have to break your lags and expose individual links, right? Just skip this. So what does it mean? It meant that I'm going to really break up all my lags, and like I said, individual links are going to get exposed. So I'm not going to have AE load balancing between two set of nodes. It also meant that I have to increase the number of LSPs. Now why? If you go back to this slide, look at the bottom side of the illustration, you would see that you have an edge node in yellow there, and just assume you have another edge node here, right? So you have AE50 and AE51. Now AE50 basically, you can safely assume, was 16 into 10 gigi interfaces, right? It is represented as one aggregate Ethernet interface. AE51 gives you another aggregated interface, and that's a set of 16 into 10 gigi links, right? And you have another PE here. So all they were doing was carrying two RSVP LSPs, one here and another here, between every edge node. So if you look at the number of label switch paths that you need in the network, it was relatively less because the links were being represented as aggregated Ethernet bundles. Now, if you break it, you're exposing every link to the system, which means the number of LSPs are going to increase quite linearly. So it meant that now we had more LSPs. So every link now had to carry an LSP. You had 16 into 10 into 2, which is basically 32 into 10 gigi links. For instance, in reality, they had 64 into 10 gigi links. So you were actually running multiple RSVP LSPs per physical link, right? Was not a very elegant solution, to be honest, when we proposed it. We said, people said, this is huge, it's a lot of state information, it's unmanageable, it's really chaotic, and so on. Honest questions, when we did the POC, if you look at it, yes, it's huge. Is it a lot of state information? What does state information mean, end of the day, for an operator? Are you going to be looking at those LSPs day in and day out? With the CLI, not really. You definitely are going to have a management station looking at that and reporting the kind of errors, link failures, and so on. But the good thing is we had a homegrown management tool developed by LINX, which could give them a much more objective output when a link failed, rather than just reporting every LSP which is getting failed. So what we actually built for them was a very static environment, which meant that we had a primary LSP going, which was strictly defined. That primary LSP was protected by a hot standby backup LSP, which again was very strictly defined, using strict EROs. So when we actually were building this, and in the POC, what we realized was, once you start building it and putting it into perspective, it's a one-time job. The big problem or the big issue here is that if you're going to be adding links in the network, and every time you add a new link, then you have to provision an LSP. And again, you have to look at whether it's the right thing to provision an LSP between two endpoints, because does the traffic, can that particular link carry the traffic? So there's a lot of thought process that needs to go in. But like I said, LINX is a pretty static environment. They are not going to add a given LINK link every other day. So it was like creating a environment for them which is like one touch. You go through the complexity day one, you provision these hundreds of LSPs in your network, and let it go. The state information, when we actually did a study and we said, what is a transit node? How many LSPs is a transit node going to be carrying? It was not really more than 1,500 or so. So every device that they were using could actually scale to, probably 64,000 LSPs or whatever. Not that I'm saying it's a good idea to have 64K LSPs in your network, but from a scaling perspective, it was not an issue. So this was pretty much what we deployed there. And there was also a plan that we had in mind saying, this is not going to be the end of the road. There should be a plan for evolving this network further. We don't want to leave you with this design for a simple fact that there are plans that more devices are going to be added. So we will look at futures, the appropriate technology, the appropriate features when they reach the maturity levels. One of the good things which I would also like to mention here is LINX, again, has a very aggressive plan to replace all these 10 gig links into 100 gig. So if you replace all your 10 gig links into 100 gig, the number of LSPs are going to drop again. You're not really going to have this large scale of LSPs that are going to be deployed, right? Pre-Olympics time is not a great time to actually have, migration which is going to say you need 12 hours every night for the next 1 month. And if they're going to tell their members that, I think they'll be out of business. So very clearly it was said that, guys, you're selling your new hardware, great, but come up with a migration plan which is seamless, which has no downtime at all. So we said, fine, let's do that. And what were the pre-migration tasks that we did? It was sort of a learning for us as well, because one of the nice things we learned out of this exercise was network modeling and capacity planning. We've always theoretically spoken about capacity planning and network modeling, and had all these nice little graphs running across, showing you what it could be, in theory and so on. But this network put us to test because we had to use, we of course used Ceridian Mate and Ceridian Collector to actually simulate the network in real time. The good thing about Ceridian Collector as a product, which we use, I would like to emphasize here, is you can put your hardware in production or in a production environment, send traffic all across in whatever scale you want, and then plug in this collector. So it's like a collector which picks up all your data real time and creates a baseline of what your network looks like. And then what you can do is create different failures which give you some kind of predictability and what to expect when you exactly have multiple failures or any catastrophe. So it was a lot of work in that sense, where we could actually come back and say, here is the different failure scenarios, here is how things would work when 1, 2, 3 links fail, and what is your worst case scenario. So we kind of knew that traffic had to be steered in the right way, in the right path, across the right LSPs. So that was one of the things which helped us put in new hardware and cater to this unknown explosion of traffic that people expected during the Olympics. On a lighter side, I think what we realized was that the Olympics never really increased any traffic on any of the networks in the UK at all. And that was very, very funny, because we were expecting that if somebody like LINX, which is carrying so much of interconnect traffic at 1.6 terabits aggregate, would probably explode to 4 terabits. And what we realized was there was hardly about few 100 megabits here and there. So, I mean, so that was what the Olympics did. So I'm not sure, I'm not here to state whether the Olympics was a success or a failure. I live in England, but I'm saying this was what we saw on the network. So, talking a little bit of the migration, you know, just trying to make it very seamless. You know, we had this overlay control plane laid, or the control plane laid in such a way that it can coexist with the present network, which means that we actually created the new address schema. Remember, you're breaking the AE links and exposing them into individual links. So what that meant was you really have to get your addressing schema right. So we had multiple secondary addresses and so on assigned to interfaces. We had our LSPs programmed in such a way that they had the right configuration in place. You know, then basically what we started doing was breaking up individual aggregated Ethernet links, and then provisioning the exact LSPs with the right addressing structure. So it was basically an activity which we did completely seamless, and that was one of the nice things about it, because there wasn't much chaos. And another thing I would like to mention is anything that happens at LINX immediately hits the press. I remember there was an outage pre-Olympics. There was a layer 2 outage, and there was this press which said Juniper lets down LINX. And there was another guy who mentioned that Juniper PTX crashed LINX's network. And you know, LINX, before LINX PR could actually get into action, we were yet to find out what the problem was. And then when we did the root cause analysis, we really found that one of the MAC filters was missing from one of the member-facing interfaces. And what happened was you had a layer 2 loop on the member's network, and he started killing off the link which didn't have the MAC filter. So, you know, it was a hard call for somebody from LINX to actually come out to the press and say, yes, this is an operational issue, this was something that we missed out, and it has nothing to do with the product. So yeah, you get good press and bad press. So this is what it looked like. Not a very rosy picture, but yeah, I think I used my iPhone to pick it up. I'm just going into where actually is LINX moving, and what are the solutions that we have when we talk to internet exchanges. Like I said, wouldn't it be nice to have RSVP do both ECMP functionality and traffic engineering? What it means is that, let's say if I can have RSVP, right, my RSVP infrastructure, to actually do load balancing on a per node basis. In other words, if I have 3 nodes connected in a sequential manner, A, B, and C, let's say I do my own load balancing, right, based on the available flows locally on the ingress router. Traffic goes to the core router, the second router. Let's say if the second router can actually be flow aware and do load balancing based on the flows independent of what the ingress router does. In other words, if a node on every hop can actually do load balancing, very similar to AE hashing, and if they can do it in a manner which is both automatic and user-defined. When I say user-defined, let's say I can have my ingress router which says I want a set of LSPs created, not point-to-point LSPs, point-to-multipoint LSPs again, which means I want to create a set of LSPs between point A and point B, and these are the set of paths I would like to prefer using constraints which are colors, or which could be bandwidth, or which could be a set of loose hops, or whatever it is. If I can do things like that, then I think it becomes very elegant. And that makes it much more easier for an operator to say, I don't need AE hashing. I don't need to have my huge lag bundles. I can signal point-to-multipoint LSPs, which reduce my state, which means I'm not going to have uh, humongous number of LSPs. I don't know if you understand what point to multi-point LSPs are. It means that I can have the ability to have just one LSP originating from the ingress node into a branch node, which is the core router. And the core router can actually fan out by creating multiple sub-LSPs. And they can either terminate on a single node or across multiple egress nodes. So that's basically what this draft, and you might want to take a look at this draft, which is there. It's been submitted quite some time back. And it's pretty interesting to note that there are multiple flavors, multiple permutations and combinations that you can use to actually achieve flow-based load balancing in proportion to the bandwidth available per sub-LSP, in proportion to the user-defined thresholds, in proportion to the physical bandwidth available, and there are different factors, and you would see different scenarios which are illustrated in this draft. You know, it's a very well-written draft in my opinion, because it's not the Greek and Latin which typically are there in internet drafts. Some of them are very, very complex to make sense. And in my opinion, this has a lot of case studies which gives you a lot of insight into what it can get. So this is a next step evolution that we have for people who want to deploy hardware or want to deploy solutions and who do not want to use AE hashing for whatever reason, and who want to look at you know, something which can actually give them both TE and you know, eCMP, and with quite a lot of flexibility as well. The other one is, like I said, fat pseudo wires. Now, fat pseudo wires again is something which is already deployed in a few places. There are some vendors who support fat pseudo wires. Juniper is yet to support it officially. Fat pseudo wire, again, like I said, is about attaching a label that pertains to a flow rather than doing any hashing. I just attach a label saying label 1, flow 1, label 2, flow 2, label 3, flow 3, send it across. I have the core router, it says, okay, I find a packet which has label 1, this means it pertains to a particular flow. The next one pertains to another flow, and it actually, you know, puts that traffic across different links. So these are basically the two areas which we see being relevant and being the next stage in evolving the way load balancing is really going to work across networks. That's it. If there's any questions, I'll be happy to take it.
Hi Vinod, one quick question, actually a couple of questions. So did you say that you deployed Juniper or replaced Brocade devices with Juniper? So when you replaced, like, how are you supporting eCMP at the moment? Because with VPLS, I just want to know how exactly you're
right now, eCMP is done through, you know, the LSPs. So basically you have equal cost LSPs which are created across the available physical links. And right now we support up to 64 eCMP paths, and which means that you can have up to 64 label switch paths or 64 physical links between a given set of nodes. In other words, 64 LSPs, and that's the way we do it.
But how do you hash into, if you have
the algorithm that Juniper or Junos uses for eCMP and AE hashing is exactly the same. So the way I create a flow, if I have an AE bundle versus having an eCMP path, is exactly the same.
So do you use pseudo wires or for VPLS? Or
VPLS uses just one pseudo wire between a given set of nodes. So if the question is how do you load balance pseudo wires, the point is yes, I get your point. So we still have to restrict one link being used for traffic being carried on one pseudo wire. So yes, so you can't get out of that. So the point is that because we have about 20 or 30 odd nodes, we feel that, you know, that kind of gets evened out, and in a sense you're able to see some kind of a traffic you know, distribution. Coming to your point about traffic belonging to a pseudo wire being spread across different links, then you have to wait or have fat pseudo wire there, because that's exactly the solution for you know, not limiting traffic within a pseudo wire to be on a physical link, but limiting a flow pertaining to a particular pseudo wire belonging to a particular link, because that makes it more relevant, because packet reordering in a flow is not, those issues are not the ideal thing. But in the present case, there is a limitation.
So one other question, does LINX has requirement for multipoint to multipoint? So if that is the case, like, do you envision some requirement in traffic engineering for multipoint to multipoint? Because at the moment it is only point to multipoint.
Yes, I mean, the thing is that I've not come across anybody in the industry at the moment who said that let's come up with a approach which is multi-point to multi-point, or create a multi-point to multi-point LSP for non-multicast traffic. Again, this is something which Cisco really pushes very hard about the need to have multi-point to multi-point LSPs for multicast traffic. And Juniper has its own view by saying we don't believe in that. We say point-to-point is better. But that apart, but there hasn't been any real need today for having a multi-point to multi-point LSP for non-multicast. A point-to-multipoint should really solve your problem. And that's exactly where the RSVP draft is going to help you, by having point-to-multipoint LSPs between a node and a separate set of nodes, or between a node and another B node, and have the ability to give you ECMP on whatever way you want, dynamic and user-defined, and also give you the ability, which is the traditional TE. Okay, so if there are no questions, thanks for attending. And
thank you very much.